All right, fantastic. So, good morning, everybody. Hopefully, you had a fantastic 4-day weekend. You enjoyed Easter or Passover, or if you don't celebrate either, then you just enjoyed some time with your friends and family, hopefully, or maybe from a distance, maybe from afar, but still, hopefully, you enjoyed yourself this weekend. It was a nice, I think, well deserved period of rest for everybody, especially after the trials and tribulations of the initial distance learning period. So, what I wanted to do for you guys today was a little bit of a test review for the upcoming summative assessment, which is scheduled for our class on Wednesday the 15th. That's April 15th on Wednesday. Okay. Just to remind you, the way that that's going to work is I am going to send out an email to you. It is actually scheduled to go out. It will arrive in your inbox at exactly 8 o'clock in the morning. That's Wednesday morning. And you will have until 6 o'clock p.m. on Wednesday to complete your work, take a picture of it, and send it back to me, just like you did for the progress assessment. Okay? If anybody, some people already contacted me, which is great, but if anybody anticipates any issue with that, like you have some other commitment for the day or anything, just let me know, and I'd be happy to work out some sort of alternate plan with you. So some people already contacted me, and we set something else up separately. So just let me know. Speaking of the progress assessment was due as of 2 minutes ago at the start of class today. I want to thank you for getting that back to me. What I'm going to do is I'm going to complete an answer key. I'm going to upload the answer key on Google Classroom, and so you can review the answer key alongside your work. And I think for the most part, that should be able to provide a good amount of feedback for how you did on the assessment, coupled with your grade on Aspen. If, however, you look at your grade, you look at the answer key, and you still have a question as to, hey, Mr. Giorgio, why did I get this amount of points off, or why did I get credit for this, or whatever, please feel free to reach out, and I'll be happy to provide you with that more specific feedback. So, just to repeat, I will upload the answer key to the progress assessment on Google Classroom. Your grade will be posted on Aspen very shortly, actually right at the end of this class. I'm going to go in there and do that. If you do have any additional questions, though, after looking at the answer key, after looking at your grade, you still want more specific feedback, I'm happy to provide that to you. Just reach out and contact me and let me know, okay? And I'll get back to you as soon as possible. Speaking of which, again, the progress assessment was submitted via email by taking pictures. That process seemed to work out nicely for just about everybody. We had just a couple technical issues here and there, but we dealt with them no problem. So I think that's the method we're going to go with in the future for submitting work. Just FYI. All right. Does anybody have any questions about the upcoming summative assessment scheduled for Wednesday the 15th? No questions? Doesn't seem as if there's any questions. Okay. One thing I actually want to mention about the assessment quickly. Oh, sorry. Peter, how much time do we have for it? So it is going to be, that's a great question. It's going to be assigned at exactly 8 o'clock a.m. You're going to get it in your inbox at 8 o'clock a.m. on Wednesday morning. And you will have until 6 o'clock p.m. on that same day to complete it and send it back to me. Just because you have a 10-hour window of time does not mean that it's a 10-hour long assessment. It is a normal length summative assessment, probably take about 45 minutes to an hour, hopefully. Maybe if it takes a little longer, then so be it. But that's how much time you'd have to get it done. Okay, so from 8 a.m. to 6 p.m. on Wednesday. Maddie says that our last summative of the year. So you may have heard with the fourth quarter grading changes that every grade is going to count equally in the fourth quarter. So there's not going to be like these little tiny progress assessments and these larger summative assessments. It's going to be more equally weighted assignments. So I guess by that logic, yes, it would be our last summative of the year, but that doesn't mean that it's your last important grade of the year because there will be more grades in the fourth quarter. Okay? Are there any other questions, concerns? Oh, one other thing I want to mention about it, while you may be thinking of other questions, is that we decided, and by we, I mean the Algebra 2 CP teachers, decided that for this summative assessment, we are only going to feature graphing radical functions and equations involving radicals. There will not be any word problems on this particular summative. The reason being is that in the midst of distance learning, some classes were able to cover it a little more in depth. Some classes didn't really get to cover it that much. We figured that in the midst of all of this unfamiliarity, that it would be for the best to just try to limit it to 2 topics to help you out as much as possible. So we're going to be focusing on, for the summative assessment, graphing radical functions and solving radical equations. Once again, there will not be any applications on the summative assessment. They are still important, though. Like, I'm glad we did them, because those types of concepts do come up in pre-calculus or other math courses going forward. So it's definitely happy that we did that together. But again, just focus on graphing and solving for the summative coming up. All right. Any other question, comment, concern about that? Okay. Let's go ahead and dive in. If you do, just feel free to type it in chat or unmute yourself and speak up. Feel free. But let's go ahead and dive into some graphing problems just to make sure we refresh our memory on how all that stuff is done. All right. Let's do it. So let's do a little bit of a graphing review. Okay. And let's start out with a square root function, something like this. If I were to try to graph a square root function, something like f of x equals the opposite of the square root of 2x minus 5, and then let's have plus 3 on the outside. Okay. So if we start graphing something like that, f of x equals the opposite of the square root of 2x minus 5, and then plus 3. Remember that when we graph these square root functions, it's all about establishing and meeting goals. Okay. So we create this little table of values, and by goals I mean we'd like to plug in values for x that help us take easy square roots. I don't want to get decimals. I don't want to make my life overly complicated if it doesn't have to be, right? Our first nice perfect square that I'd like to aim for is the square root of 0. I'd like to find, because that's the first perfect square in the list, I'd like to find out what number I can plug in for x such that I can take the square root of 0. So what number, if I plug this in, allows this middle part to come out to be 0? Well, you might think to yourself, I don't know. I don't know what makes that middle part equal to 0, but don't worry, we can go ahead and make a little equation. We can figure out, well, when does 2x minus 5 actually equal 0? When does that occur, right? Well, if we add 5 to both sides, we get that 2x is equal to 5. Divide both sides by 2, you get x is 5 halves, or 2.5. Okay? If you prefer 2.5, you can write 2.5. All right? So, again, if you can't see that off the top of your head, you always have that fallback strategy of, well, let me just make a little equation off to the side and figure out what value for x is going to satisfy that part under the square root. Now that I know that, by the way, I can go ahead and plug in 5 halves, or 2.5, under here. You know that if you do that, you're going to get 0 under here. That was the point of picking that, right? The 2 divided by 2 times 2 divided by 2 cancels out. 5 minus 5 is 0. The square root of 0 is still 0. The opposite is still 0. Plus 3 is 3. So your starting point is going to be at 5 halves, or 2.5, comma 3, right? Remember, we refer to this as our starting point. Does that make sense to everybody, hopefully? Okay. If you have a question, again, please feel free to interrupt or just type in the chat. The next perfect square we'd want to look for is the square root of 1. I want to figure out what value should I plug in order to get the square root of 1. I think this one I can see off the top of my head. It should be 3. Because 2 times 3 would make 6, minus 5 is 1. But once again, if you can't see that, you could always go ahead and be like, let's find out when 2x minus 5 is equal to 1. Let's find out when this inner portion underneath the radical equals 1 by adding 5 to both sides. You get 2x equals 6, and divide by 2, you get x is 3. Okay? So you could always rely, once again, on that failsafe. All right? You know that if you plug in 3, this middle part's going to come out to be 1. The square root of 1 is 1. The opposite is negative 1. Plus 3 is 2. Okay? I then am looking to take the square root of 4, because that's our next perfect square. Notice I wouldn't shoot for the square root of 2, because the square root of 2 is a decimal. I'd rather avoid that if possible, right? So what number allows me to take the square root of 4? Again, we can make a little equation. Say, well, when is 2x minus 5 equal to 4? Let's add 5 to both sides. We get 2x is equal to 9. Divide by 2, you get x equals 9 halves, or 4.5. Okay? You know that when you plug in 9 halves, you're going to get 4 under here. That's why you picked it. The square root of 4 is 2. The opposite is negative 2. Plus 3 is positive 1. And last but most certainly not least, we're looking to take the square root of 9. Again, you could keep going if you want to, the square root of 16, square root of 25, square root of 36, but for our purposes, we usually stop at 9. It's enough to give us a nice picture. What value can we plug in for x in order to get 9? I think I see it again off the top of my head. That's 7, because 2 times 7 would make 14, minus 5 would make 9. The square root of 9 is 3. The opposite is negative 3, plus 3 is 0. Hopefully everybody's paying attention to the order of operations as I'm evaluating. Okay? Does anybody have a question as to how we generated this table of values? Questions at all? Everybody's doing good. Okay, very good. Now we can go ahead, of course, and graph this stuff. So I'm going to do exactly that. I'm going to sketch a little graph. Should be enough room to plot everything. We have our first point, our starting point at 2.5, comma 3, 1, 2, 3. We have our next point at 3, comma 2. We have a point at 4.5, comma 1, 1, 2, 3, 4 and a half, comma 1. And we have our last point at 7, comma 0, 1, 2, 3, 4, 5, 6, 7, comma 0. And we end up with this square root function that looks like that. Okay? No questions, hopefully, as to how we graph that. Yes, just plotting points. A couple things that we have to specify when it comes to graphs is we do have to remember to indicate the transformations as well as the domain and range. So let's start with the transformations. Again, what the transformation is asking is how does this function that we just graphed differ from the parent function being the regular old square root of x. The regular old square root of x looks like this, right? So how does this function that we just constructed differ from this? Well, the starting point is definitely in a different spot. Instead of starting at 0, 0, the origin, this new graph moved over to the right 2.5 units, right? So we could say it went right 2.5 units. It also went up 1, 2, 3 units, so up 3 units. Okay? And because of that negative out in front there, you could say that it has a stretch of -1, or a more descriptive thing that you could say is you could say it reflects over the x-axis, meaning that it flipped upside down over the x-axis, just flipped upside down. Okay? Does anyone have a question as to the transformations? Hopefully that makes sense. Okay, let's move into the domain and range quickly. Again, domain refers to the possible x values for the function. Visually, it's where the function is positioned with respect to the x-axis. The furthest to the left that the function goes is 2.5, or 5 halves. And the furthest to the right the function goes, well, it goes forever, so you would say that we go to infinity. Okay? Notice again that I use that square bracket to include 2.5 and the parenthesis to exclude infinity. We never include infinity. You can never count to it. I was just about to write infinity. We're now looking for the range. The range does have an infinity in it. It starts at negative infinity because the range refers to how far down does the function go and how far up does it go. Well, it goes down forever, but it doesn't go up forever. It goes up to 3. Okay. Cool. So that would now be a complete graph with information for a square root function like that. No questions, comments, concerns about that? Alrighty. Let's transition to another graphing example. Let's do a cube root this time, maybe one that involves a little bit of a GCF and simplifying, okay? How about something like f of x is equal to 3 halves, don't freak out, don't panic, it's just 1.5 times the square root of 8x plus 16, and then minus 1. Okay? Maybe something like this. Well, you may notice when you try to jump into this problem that it looks horrible and it looks annoying and it looks ugly. Sorry, problem, I don't mean to offend you, but this is horrible. This is all sorts of ugliness in here. I'd much rather try to simplify this before jumping right in so I can deal with all that ugliness. Now, do you have to simplify? No, you could actually go right in and get a valid graph, but that process is so much more difficult than if you notice, ooh, there's a GCF, and you go about your simplifying process. You'll see, watch. You'll see how much this is going to simplify and make the problem a lot easier. First of all, on the inside, we'd be able to take out a greatest common factor of 8, leaving us with x plus 2, and then minus 1, because 8 times 2 is 16. The benefit of doing that is we now have the cube root of 8 times x plus 2, which is equivalent to the cube root of 8 times the cube root of x plus 2. Okay? And now you may notice, ooh, well, the cube root of 8 is just equal to 2. So this really comes out to be 3 halves times 2 times the cube root of x plus 2, and then minus 1. And what's 3 halves times 2? Well, the 2's will cancel out, and you'll be left with 3 times the cube root of x plus 2 minus 1. Okay? Does everybody see that? And now you look at that, and you're like, wow, that's way easier to deal with than dealing with all this. Okay? Does anybody have a question as to how we were able to take something like this and simplify it down to look like this? Hopefully we're all feeling good about that. Okay? Again, if you have a question, just feel free to ask. Now, what we can do is, just like before, we can go ahead and make a little table of values and then sketch a graph. So I'll do my table. I think I should have enough room right over here. Create a little table. Much like the square root function, the cube root function is going to be still reliant on those goals, but not reliant on the 0, 1, 4, 9, which were the perfect squares. Instead, now we're going to be aiming for the perfect cubes. Remember, you can take the cube root of both positive and negative numbers. So we're looking for the cube root of 0, the cube root of 1, the cube root of 8, because those are nice, easy numbers. And in the negative direction, the cube root of negative 1 and the cube root of negative 8. Okay? So now that I'm doing that, we're looking for what value should I plug in order to get the cube root of 0. So to get the cube root of 0, I'm looking to plug in what into this function? It looks like negative 2, right? Because negative 2 plus 2 is 0. The cube root of 0 is 0. Times 3 is still 0. Minus 1 is negative 1. So everybody see that? The cube root of 1 now we're looking to get. I believe I have to plug in negative 1 in order to make that happen, because negative 1 plus 2 is positive 1. The cube root of 1 is 1. Times 3 is 3. Minus 1 is 2. Next, to get the cube root of 8, well, let's see, what value do I need here? It looks like 6, because 6 plus 2 would be 8. The cube root of 8 is 2. Times 3 is 6. Minus 1 is 5. Okay. Remember to actually take the cube root of 8. A lot of students make that mistake of saying, oh, well, the cube root of 0 is 0. The cube root of 1 is 1. Those don't change per se. But then the cube root of 8 does. The cube root of 8 is 2. So don't forget that little step. Okay. Trending in the negative direction now, we can go ahead and say, well, what value can I plug in to get negative 1? That's going to be negative 3. Because negative 3 plus 2 is negative 1. The cube root of negative 1 is negative 1. Times 3 is negative 3. Minus 1 is negative 4. And last but most certainly not least, to get negative 8 up here, it looks like I'm going to need negative 10. Because negative 10 plus 2 is negative 8. The cube root of negative 8 is negative 2. Times 3 is negative 6. Minus 1 is negative 7. Okay. Does anybody have a question, comment, or concern as to how we graphed that, or how we generated that table of values? We didn't actually graph it yet. We're good on that? That makes sense to everybody? Seems logical? Now we can go ahead and sketch a graph of that. Unfortunately, I kind of ran out of room over here, so we're going to throw a new piece of paper down here so we can actually go ahead and sketch a graph. Let's see what this graph is going to look like. We're going to need a lot of room here because it looks like we go pretty far in the negative direction and pretty far in the positive direction. So I go ahead and sketch a graph of this. We have our center point. Remember, this is called our center point because the cube root extends outward in both directions, right? As opposed to the square root, which kind of starts somewhere and continues in one direction. The cube root goes in both directions from a center point. So we're starting at negative 2 comma 1 right here. Oh, sorry, not right there. Negative 2, negative 1 right there. We're then going in the positive direction to negative 1 comma 2 right here. We have 6 comma 5 as well. That's 1, 2, 3, 4, 5, 6 comma 1, 2, 3, 4, 5. In the negative direction, we have a point at negative 3 comma negative 1, 2, 3, 4 right there. And we also have a point at negative 10 comma negative 7. So negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 comma negative 1, 2, 3, 4, 5, 6, 7 right here. And if you notice, ignore that little point, but if you notice, all of these points, when connected, resemble that S shape that you should expect to see with the cube root function. They always come out to look like these little S shapes, whereas the square root functions always come out to be these little swooshes, right? So, looking at something like that, you should be able to identify that that's a cube root function. Like, that should make sense. That should check out in your mind as being like, ooh, this looks like what it's supposed to look like. And that should be a good confirmation for you. Okay? A couple other pieces of information about this graph. Of course, we have the transformations. Just like with the square root function, how we look at the starting point to determine the transformations, we do the same with the cube root function. We're just going to look at the center point now to say, well, this graph compared to the parent function went left 2 units. It also went down 1 unit. And unlike the parent function, which has a stretch of 1, this now has a stretch of 3, meaning it's increasing and decreasing 3 times as quickly. So I'm going to say it has a stretch of 3. Okay, just like that. We also have the domain and the range, but there's really not too much to say about the domain and range of a cube root function, because you should be able to identify it's always 100% of the time all real numbers, because no matter what cube root function you have, it's always going to extend left and right forever and up and down forever. Okay. Any question on either of those two graphing problems? I wanted to make sure I spent the majority of our time today on the graphing problems, because that was probably the thing that we had done, less recently than we did solving equations, right? Solving equations should be fresh in our mind. We just had our progress assessment on it. Graphing was probably a little rusty, so that's why I wanted to revisit it with you as far as the majority of our time was concerned today. But that doesn't mean we have to forget about our friends, our equation friends. So let's go ahead and just solve some equations quickly, okay? Let's go ahead and solve some equations quickly. How about something like this? Ready? I should be able to, we got what, 8 minutes? We can do 2 equations in 8 minutes. We can do 2 equations. Let's start with one like this. How about -5 is equal to the square root of x plus 15 and then minus x. Okay? If we start with a problem like this and we're trying to solve this equation for x, the very first thing you're going to want to do is isolate the radical. So to isolate the radical, I'm going to go ahead and add x to both sides. That gives me x minus 5, or you could write it as -5 plus x if you prefer, is equal to the square root of x plus 15. Now that I isolated the radical successfully, we can go ahead and square both sides to eliminate that square root, because I need to get to that x under that square root. So we can square both sides just like this. On the right side, the square root and square cancel out, but on the left side, remember to do x minus 5 squared. We have to take x minus 5 and multiply it by itself, and that gives us x plus 15 over here, because the square root and square cancel. Now we do a little first outer inner last distributive property here to get x squared minus 5x minus 5x minus 10x, and then minus 5 times minus 5 plus 25 is equal to x plus 15. You see that value of x squared show up. That should be an immediate indicator that we need to factor. Okay. In order to factor, though, we have to set equal to 0. So I'm going to subtract my x over there. I'm going to subtract my 15 over here. That gives me x squared minus 11x, and then 25 minus 15, so plus 10. Okay. Now a little bit of factoring. You know that we need x and x to make x squared. Since we're multiplying to a positive, we need both of the same sign. And since there's a negative in the middle, it makes sense to make both negative. And what factors of 10 are going to combine via distribution to make my -11? It's going to be 10 and 1. Okay? That gives me 2 potential solutions, one of x equals 10 and one of x equals 1. Now, of course, you may think, oh, well, that's great. We got 2 solutions. Or did we? That's the question. We have to remember to check for extraneous solutions, because it can definitely happen. Let's check when x is equal to 10. Is it true, we're going way back up to the top to plug in here, that -5 plus the square root of 10 plus 15 minus an additional 10, oh sorry, -5 is equal to, sorry, I think I misspoke. Is it true that -5 is equal to the square root of 10 plus 15 minus an additional 10? I believe this works, right? -5 should equal the square root of 25 minus 10, because that's 5 minus 10, and that's definitely equal to -5. So I'm happy with that. Solution of x equals 10 works out. How about x equals 1? Let's check when x equals 1. Is it true, again going way back up to the top, that -5 is equal to the square root of 1 plus 15 and then minus an additional 1? I'm not as convinced on this one. I'm not as convinced on this one. Negative 5 is equal to the square root of 16 minus 1. Square root of 16 is 4, minus 1 is 3. Definitely not equal to negative 5. So we do have one extraneous solution. But we do at least have one real solution, and that one real solution is x equals 10. Okay? Any questions, comments, or concerns about that? That's definitely a standard difficulty radical equation that you should be expected to do on any sort of assessment. All right? I also want to do a double radical equation with you. We have about 4 minutes to go. It may take slightly longer than the 4 minutes, so if you have to leave right at 11:10, I understand, no judgment. But I am going to go through it with you because I think it is for your benefit. Okay, just a couple of reminders again before I jump into it, because it might take us past the scheduled end time of class, that your summative assessment will be arriving in your inbox at 8 a.m. on Wednesday, April 15th. You'll have until 6 p.m. to complete it, take pictures, and send it back to me. Okay? If you need any clarifying information, please feel free to reach out. I'm going to send that information that I said today via email so you can review that and make sure you are reminded of that. But again, feel free to reach out if you have any questions to either myself or Ms. Mao as well. All right, so let's deal with our last double distribution problem, and then we'll be good for the day. We got the square root of 3x minus 3 is equal to the square root of 5x minus 4, and then minus an additional 1. Without that minus 1 stuck onto the end, this would be a great problem, because then we could just square both sides and eliminate both radicals right away. Unfortunately, because you have that constant stuck onto the end of the radical there, it's impossible to isolate both radicals simultaneously. The minus 1's either going to be stuck over here, or if you add 1 to the other side, well, then it's stuck over there. So we just kind of have to deal with it. That's okay, though. We can square both sides once to eliminate one of the radicals, and then square both sides again to eliminate the other one. Notice the left side, the square and square root are going to cancel out, and I'm left with 3x minus 3. On the right side, however, we need to take that binomial and multiply it by itself. I have the square root of 5x minus 4 minus 1 times itself, times the square root of 5x minus 4, and then minus 1. Okay, that's going to require a little bit of distribution. So on the left side, we still have 3x minus 3. On the right side, though, I'm going to do 5x minus 4 times 5x minus, the square root of 5x minus 4 times the square root of 5x minus 4 is just 5x minus 4. Because that's the square root of 5x minus 4 times itself, or in other words, the square root of 5x minus 4 squared, which is just 5x minus 4. Here I have the square root of 5x minus 4 times negative 1 on the outer multiplication. That's exactly that, negative 1 square root of 5x minus 4. Same thing on the inside, the opposite of the square root of 5x minus 4 again. And then last, negative 1 times negative 1 is positive 1. Okay? I'm going to clean up the right side of the equation. Left side's still staying the same, 3x minus 3. Here I have a 5x. That doesn't really combine with any other terms. I have a negative 4 and a positive 1, so altogether that makes negative 3. And that's going to be connected to this additional negative 2 square root of 5x minus 4. Because if you notice, I have negative 1 of these square roots and another negative 1 of these square roots, so altogether that makes negative 2 of them. Now, a very common student misconception is a lot of people will be tempted to do, ooh, negative 3 minus 2 is negative 5. But not the case. Please, please, please do not do that. Remember, this negative 2 is connected to this square root of 5x minus 4. It's just like if you had negative 3 minus 2x. You wouldn't stick those together and make some hybrid term. It's the same exact thing here. But we do have one radical now, which is great. So I can go ahead and isolate it and square both sides. I'm going to add 3 over to this side. Ooh, kind of convenient that the 3's cancel out. That's nice. That's going to save me some work. Subtract 5x over to here. I get negative 2x is equal to negative 2 times the square root of 5x minus 4. Ooh, this is really best case situation here, because if you remember, at this particular point, I implored you to look at the coefficient of the radical and say, hey, is it possible to divide both sides by that coefficient to simplify things? And if not, then at least divide by a GCF or something. And in this case, it absolutely is. Negative 2 divided by negative 2 is just 1x is equal to, here the negative 2's cancel out, the square root of 5x minus 4. Now, if you can't do that division, it's not the end of the world. You do have to square with that coefficient out in front there. But all you would do if I squared this whole thing, it would be negative 2 squared is positive 4 times 5x minus 4. Because the square root of 5x minus 4 squared would be 5x minus 4. Okay, so if you couldn't divide, again, it's not really throwing my pen, I'm getting excited. It's not really the end of the world, but it does make it a lot more convenient if we can. Now I can go ahead and square both sides to eliminate that last radical. Should be pretty straightforward at this step. X squared equals 5x minus 4 because the square root and square cancel out. We see that x squared, prime time indicator to factor. Subtract 5x to this side and add 4 to this side. We got x squared minus 5x plus 4 is equal to 0. I can go ahead and factor that down nicely to be x and x to make x squared, 2 negatives to satisfy my signs, and we have minus 4 and minus 1. That gives us two potential solutions, one of x equals 4 and one of x equals 1. Okay, sorry, I had to squish it right at the bottom there. Of course, we do need to check for extraneous solutions, so let's make sure we check. When x is equal to 4, is it true? We're going to go way back up to the top here, and we're going to check. Is the square root of 3 times 4 minus 3, is that equal to the square root of 5 times 4 minus 4 minus an additional 1? I'm just taking 4, I'm plugging it in for all the x's. Let's see, we get the square root of 9 here, which is just equal to 3, is equal to the square root of 16 minus 1. I think that works out, right? I think that works out very nicely. So we get that 3 is equal to 3, and we're happy with that. Okay? Now we can check one more time. If x is equal to 1, is it true that the square root of 3 times 1 minus 3 is equal to the square root of 5 times 1 minus 4, and then minus an additional 1? Here I get the square root of 0. Here I get 5 minus 4 is 1 minus 1. Yeah, that looks great. Square root of 1 minus 1, also 0. So I'm happy with my two solutions, both of which check out in this case. We get two solutions, one of x equals 4 and one of x equals 1. They both work out nicely. All right. Does anybody have any questions, comments, concerns about that at all? Feeling good? Hopefully. I didn't get a chance to look at this class's progress assessments yet because they weren't due prior to they were due at the start of class, so I'm going to go ahead and take a look at them now. But I did look at my other classes' progress assessments, and a problem like this, a double distribution problem, was definitely the biggest cause for concern. So please make sure that you, if necessary, go back to watch the other video lessons to see problems done out like this. There's definitely going to be one on the summative assessment. That's why we're talking about it a lot. So hopefully these steps made sense, but if they don't, please go back and try some on your own. It's really great practice and only to your benefit. Okay? So thank you so much for your attention and focus today. I appreciate that. I hope you have a fantastic rest of your day, and I will see you on Wednesday for a summative. All right? Study hard. Reach out if you have any questions. Good luck.